In Chapter 10, we turn our attention to hypothesis testing with two samples. Chapter 9 was strictly hypothesis testing involving one sample, and in Chapter 10 we move on to two samples. Now there's a lot of good reasons why we would want to test with two samples. In the real world, quote unquote, there's a lot of situations where we are comparing two groups. Anytime a new medication is being tested, they usually use two groups of people, one that's receiving the medicine and one that's getting the placebo, so that they can compare results and they can compare side effects and all that kind of stuff that they need to be aware of before they can release a new medication. There's lots of statistics and reference to things like salaries of men and women being different, men being paid more than women for the same work. There's crime rates in different cities might be compared, and then more of a before and after type of scenario might be involved, like a weight loss program where we take people's weights before and after. So that kind of data is what we call matched or paired data, where we have the same subject being surveyed twice, and we're comparing to see if there's any difference. So in this chapter, there's a lot going on. We're going to start out just trying to make sure that we understand what type of hypothesis test we're supposed to do in each scenario. And then we're going to do hypothesis tests for independent samples from populations. We're going to do it both with a known standard deviation and an unknown standard deviation. And then we're going to test hypotheses for proportions. And then we're going to do, kind of like the before and after example I was talking about a moment ago, we're going to conduct hypothesis tests for matched or paired samples. So beginning with section 1, we're going to test two population means with an unknown standard deviation, or I should say unknown standard deviations, plural. Okay, there's two different populations here, and so they have two different standard deviations, and we don't know what they are. Okay, so here are our set of criteria that we're going to use to establish that we're using the correct test. We've got two independent samples that are collected using simple random sampling, and they're from two different populations, that we can identify. They're distinct, right? We can tell them apart. And for these two distinct populations, we have to be careful. If the sample size is small, then the populations need to be normal. Okay, they need to fit a bell curve. But if the sample size is large, then the distribution we don't need to worry about it. Okay, and remember that the whole reason for that is from chapter 7 with the central limit theorem. The central limit theorem said that the means for samples will be normally distributed as long as the sample size is sufficiently large. So there's that central limit theorem coming back in a direct application. So what we're actually testing here, once again, the null hypothesis is the thing that we're going to directly test mathematically. Okay, we're going to look for a p-value that describes the probability that we got a result given that the null hypothesis is true. And in this case, the null hypothesis will always be that the two population means are equal. Okay, or you can say it a different way. You could say that the null hypothesis is always going to be that the difference between the two means is always 0. Okay, so in fact, if you look through the examples in the textbook, quite often they write the null hypothesis and the alternative hypothesis two different ways. One of them will say like mu1 equals mu2, and the other one will be mu1 minus mu2 equals 0. Okay, they mean exactly the same thing. You can choose either way. In the examples that I have written in these slides here, I just picked one. If you look in section 1 in the textbook, there are some pretty complicated formulas for things like finding the t-value, the t-score, for things like finding the standard error. The formulas are kind of ugly. So we're going to use the calculators to actually perform the tests. So there's no need to memorize any nasty formulas. We really live in a day and age where between your calculator and all sorts of math software that's available to you, things like Wolfram Alpha and Maple and SAS and all these things. There's so many math programs out there that there's really no need to memorize formulas and calculate these things by hand. So for this particular test, we're using a student t-test with 2 samples. So the function in the calculator is the 2samp t-test. It's in the same menu as all the other tests that we've been doing, so it should be easy to find. But just be careful because there's a 2samp z-test and a 2samp t-test. So remember, if you do not have the population standard deviations, then you're using the 2samp t-test. For our first example, the average amount of time boys and girls aged 7 to 11 spend playing sports each day is believed to be the same. Study is done and data are collected, resulting in the data below. Sorry about the repeated phrase. Each population has a normal distribution, so our samples are not real big, okay, so it's important that they're telling us that the population is normally distributed. That's good. So you can see the numbers in the table there. Is there a difference in the mean amount of time boys and girls aged 7 to 11 play sports each day? Test at the 5% level. Okay, so to begin with, we have the sample standard deviations, but we don't have the population standard deviations, so this fits the t-test scenario, okay, the 2samp t-test. And we need to think first about what our null and alternative hypotheses are going to be. Okay, anytime we're doing hypothesis testing, whether it's 1 sample or 2 sample, the first thing we should think about is the null and alternative hypotheses. So the question we're being asked is there a difference in the mean amount of time boys and girls, yada yada. So is there a difference? So it's not asking is one greater than the other, or is this one less than that one. It's just saying, are they different? So our null hypothesis will be, like I told you it will be either we could write mu1 equals mu2, or we could write mu1 minus mu2 equals 0. The alternative hypothesis, because there's nothing specified about greater than or less than, it's just is it different, we're going to say that our alternative hypothesis is not equal to. So on the next slide, we're going to keep working here. Here's the null, and I wrote it as mu g for girls and mu b for boys. And then there's our alternative hypothesis that mu g minus mu b is not equal to 0. So now you want to go to the student 2samp t-test in your calculator, and you want to put in all that information that was in this table. So you might want to go back and view the table. The numbers in the table are not in the same order that you need to put them in. Excuse me, need to put them in your calculator. So just as you're doing these, be very careful not to go too fast and get the order wrong. So the order we have to put them in is the x bar 1, so the first sample mean, and then sx1, which is the first sample standard deviation, and then n1, which is the sample size. So not in the correct order for the table, so be careful. But what you should get, oh, and by the way, when you do 2samp t-test, one of the things it asks you at the very bottom is pooled, no, or yes. And we are always going to say no. Okay. This question has to do with, is the standard error pooled? And what that means is, are we combining the 2 standard deviations together, or are we going to treat them as possibly different? Are we going to treat the standard deviation of one sample as different from the other? And we want to treat them as different. Statistics research has shown that it's a more reliable method if you think there may be a difference between the two. And we don't know for sure, so we think it's possible there could be a difference between the 2 standard deviations. So we're going to say pooled is always no. Alright, so when you hit enter, or when you hit calculate and then enter, you get a p-value of 0.0054. So that is significantly less than our alpha, which we were told to use the 5% level, so that would be 0.05. So since the p-value is low, we reject the null hypothesis. And so our conclusion is that the mean time that boys and girls spend playing sports in this age group is different. Okay, they do not spend the same amount of time playing sports. For section 1, the practice 1 through 5, that part is just selecting the right the right distribution to use. So you may need to read some of the information in that section between the chapter title and the actual start of section 1, because there's some information in there about what the different distributions might be. So for 1 through 5, all you're doing is selecting the right distribution. Be kind of on the lookout for ones that fit student T, okay, since that's what we discussed in section 1. And then the 78 through 80 from the homework section, those are more hypothesis test examples that you can actually work. So let me know if you have any questions on this, and good luck.